I'm Steve Pope, I'm Fellow at Xilinx, and I run the Data Center Networking Architecture Group. I'm going to talk about our new Composable SmartNIC architecture. It's a key part of the SN1000 SmartNIC. So this is zooming in one layer deeper and kind of narrowing the focus a little bit from the kind of all-encompassing data center composability that Ivo was talking about. I'm going to talk about some of the challenges of building the NIC itself. And then I'll hand over to Martin Porter, who's going to illustrate the architecture and provide some more detail on the SN1000 implementation. Okay, so if you didn't watch it, I'd recommend last year's Hot Chips debate. It was entitled, "What's a Smart NIC?" And amazingly, that's still a question. It's still quite a very valid question that causes a lot of confusion. Now, in many ways, smart is just a superlative. It indicates higher value coined by marketing guys. So I wanted to start with a kind of very coarse functional taxonomy here. So a regular NIC, it does all the processing up to ISO layer 3. Right? And that in itself may require quite sophisticated parsing, switching, and cryptography for overlay protocols. And there's nothing dumb about that. Regular NICs can also contain premium functions such as security telemetry or an optimized host interface. The Solarflare NICs contained a host interface optimized for user space, very low latency, high message rate TCP. Now, the key distinction of smart NICs is that they support upper layer application processing. And for network-centric applications, such as storage virtualization, these applications that have been brought onto the SmartNIC are typically part of the hypervisor. Now, SmartNIC adoption to date has, in fact, been driven by accelerating hypervisors, moving them basically from the main server CPU to the NIC. Now, just moving the hypervisor provides quite a simple but very effective performance benefit, because without the hypervisor on the server, we just remove the virtualization tax on the instruction stream of that server. And that's just moving, no fancy offloads required. So in this regard, we can consider the SmartNIC as being just a CPU in front of the CPU, in front of the server CPU, performing those upper layer application processing tasks. However, the overall architecture here is bumping the wire. So it puts a significant burden on the SmartNIC. And in the worst case, we can see the NIC having to handle double the bandwidth of the server that it's fronting. And the backdrop of all this is we're trying to upgrade the network to terabit speeds. We're seeing PCI rapidly moving on to Gen 6. We can see Ethernet moving on to 400 gigs. We have the bandwidth. It's more of a question of, can we use it effectively at the endpoint? And so at these speeds, application acceleration and the workloads is becoming a very interesting problem to solve. And so for all these reasons, we're seeing the emergence of domain-specific processing architectures for smart NICs. And the Xilinx SmartNIC is a composable architecture. It is a domain-specific architecture. And the key point about it is that we're using programmable logic to enable those processing efficiency gains. So to illustrate the performance and power bottlenecks of smart NICs, I wanted to first look at what you might call the first generation SmartNIC. These have got very general purpose CPU-centric architectures internally. Here we go. Now, most processing is performed on the embedded CPUs. These standard general purpose CPUs, ARMs typically, they execute existing hypervisor code packages which are ported to a standard system environment. Now that's good because you get feature velocity and flexibility. It's basically the same environment as previously existed on the host. However, you can be quickly bottlenecked by CPU cores, especially as NICs have got very constrained power envelopes in which they have to operate. Now, the CPU is synchronized with the rest of the data path through DRAM, and accelerators are loosely coupled. And so the control and some of the data tends to flow back and forth between the CPUs and the accelerators. And that means the DRAM bandwidth and power is another bottleneck that we see on SmartNICs. Now, recent SmartNICs include both fixed function and programmable hardware accelerators. And that's great because these enable higher packet rates and increased bandwidths. But fundamentally, the silicon is a scarce resource, and there's just no one size that fits all here. Programmable accelerators are often limited by the expressiveness of their individual programming models and by the fixed hardware structures that surround them. As I said, control is often passed back to CPUs, and this often occurs at the protocol layer or software subsystem API boundaries. This just exacerbates the bottlenecks, particularly with regards to cache pollution. And so, to avoid these bottlenecks, what we'd really like to do is distill out the control plane so that there's general purpose CPUs, and this is kind of very similar to the point John was making with Ivo's talk, that these general purpose CPUs are really only there to execute the control operations, leaving the data plane intact and allowing data to flow smoothly from the network through to the host. Okay, so our architecture has got three goals then. Right? The first is to just achieve line rate performance for a wide range of applications with differing requirements. And that line rate is rapidly increasing, as I said, from 100 gigs to 400 gigs. We want to adapt to new applications and workloads that might arise in the future. And we want to be software definable. Now, of course, software definable means all things to all people, but what I mean is in two aspects here. The first is to provide a framework by which the NIC itself can be extended to support the hardware accelerated APIs in a manner that's natural to the applications. And then, what that also means is that we just don't want to see applications be rewritten. Right? I mean, that's just like boiling the ocean. And the second point is to enable software tools to define and provision the most optimal hardware for the applications. And that's the other way around to the way the world actually is most of the time, where software, what we want is that software defines the hardware, right? We don't want hardware to dictate a programming model to software. So this diagram is the composable SmartNIC architecture. It's built around the data plane. As I say, we want data to be flowing smoothly from the network to the host. And the data plane comprises a set of standard blocks or accelerators. Now, these provide functionality such as PCI itself, DMA, different DMA types, stateless offload, such as transmit segmentation offload, crypto, Ethernet, MAC and PHY itself. These are all the standard blocks of the data plane. We have a set of onboard CPUs. These provide standard operating system environment and threading model. Software running on those CPUs can interact with the data plane using shared memory or key pair abstractions. Xilinx provides runtime driver and firmware support for all of that and for standard operating system environments. And Martin is going to later show how the hardware-software interaction, because that's key here, all comes together with a storage virtualization example. DRAM can be used by all components in the data path to buffer or store persistent state, such as flow tables. And then uniquely, we're using programmable logic. And this allows the application-specific logic to be inserted to form the application-specific data path. It provides the glue for an instance of that data path. So with our approach, we can accelerate entire applications, and we can fully separate out the control and data plane processing. And our application-specific data planes can be composed on the fly from a mixture of standard and application-specific accelerators, which all may be using different technologies, such as fixed function ASIC, domain-specific CPUs, or programmable logic. And this flexible chaining of the data plane components allows program state to be passed along that data plane without requiring CPU intervention to execute any control plane logic. And the components themselves are programmable, and they can be programmed using high-level and domain-specific languages such as P4. And the components are designed to map naturally onto the major APIs within those embedded CPUs. And those APIs are things like BSD sockets, SPDK, or the Linux XDP.
I had a question on the previous slide. It's not a very specific question, but I'm just kind of like wondering my use cases, like how can I leverage FPGAs? And I'm concerned with things being read off the wire very quickly. If we're using FPGAs on a log ingestion, right? Typically, if we want to do high volume log ingestion, there's a lot of data manipulation that happens in logical pipelines, right? We want to change various fields and things like that before that log data is written either to database or to disk somewhere. Would that be a practical use case, is being able to maybe offload some of that data manipulation and transformation and do it at the SmartNIC level so that we don't have to do that through the CPU? Yes,
absolutely. So the idea is that the SmartNIC can offload applications themselves. And in your example, the logging function is at the application layer. And what you would be able to do is express those transforms. And P4 is great, and we talk a lot about P4, but it's very specific for network protocol processing. For the kind of transforms you're talking about, it may well be that expressing that in another quite high-level language like C or C++, and then using the HLS synthesis flow, would allow a SmartNIC component, and actually on this slide here, I'm showing the components of the SN1000 data plane, but you could build a component that implemented your logging application, or at least the fast path pieces of that application. And the data and that component can be inserted dynamically on the fly into the SmartNIC data path and perform that processing inline at wire speed without any of that ever touching the CPU. And then the SmartNIC would have the intelligence to, do the right thing as the output of that processing. It may send it and re-encapsulate it and send it somewhere else for persisting. It may persist it locally, or send it, very, very intelligently to the host to be consumed.
So as another sort of potential use case, again, and this is just relevant to me and my work, typically when we build and deploy like an IPS system, the bottleneck is that we can't run signatures, thousands and thousands and thousands, maybe 100,000 signatures against every packet that comes through at line rate. I may have 10 gig NICs on my host, but I can only process at the most maybe 2 gigs throughput through the CPU, leveraging CPUs, even if we do some tuning with CPU pinning for the application. Would we be able to offload some of that signature identification to a SmartNIC, freeing up the CPU to do other things on those systems?
Yeah, yes, again. Because the SmartNIC, I'm not showing any protocol components here, but Martin later on will show that with our storage virtualization example, he's going to show TCP and a Ceph distributed object storage bridge, so Ceph being the high-level application. Now, you could be above TCP layer, you could be inserting a component that had those IDS rules. And what, as Vivo is pointing out, one of the really nice features of FPGAs for this kind of thing is just the incredible parallelism that you get. And so that entire data plane can be spread out and executed in parallel against your rule set. So IDS is definitely a key application that SmartNICs are actually quite good at.
Steven, I have an additional question following Tony here. So we are talking about a SmartNIC, so a specific component in a traditional architecture, server architecture. You are meaning somehow that with a SmartNIC with enough FPGA, I can remove the FPGA card that I have to buy to do all these additional compute operations. because somehow, we are talking about very high level operations, even, checking on signature, logging or whatever. So it's application level, and it's not low level like networking stuff. So is it so sophisticated that I can use the same FPGA that you deliver in the SmartNIC to do something else?
Oh, absolutely. Yeah, the whole point of a SmartNIC is to ingest application workloads. That's what makes it a SmartNIC in my mind. And everything up to layer, in fact, everything up to the transport layer, think of it as being functions of the composable data plane. They can be mixed and matched according to particular applications. But then from that point on, you can continue to compose the data plane with the application-specific components, and even have applications which fully terminate the data. We don't have to be. I'm showing here data being delivered from the network to the host, but data can be completely terminated by a SmartNIC component. You do have that extreme flexibility. So this slide is showing an instance of the architecture. It's the SN1000 composable data plane, and I'll walk through the key components here. First is the transmit DMA component. This implements all the DMA device personalities for the SN1000, and we're supporting VirtIO keypad types. VirtIO was designed for hypervisors, for a power virtualized interface between the guest operating system and the hypervisor. And then it was adapted particularly for bare metal environments to implement the same interface at the hardware level over PCI. So we support this at the hardware level in hardware, very high performance. We also support QDMA, which is a very generic multi-queue DMA. It's used for lots of custom applications. And we support EF400, which is the next generation of the solar flare device type, which is oriented for high performance networking. Also in this block are networking operations that are entwined fundamentally with descriptor processing. So things like transmit, segmentation, offload for TCP. To perform that operation, you really need to understand all the DMA descriptors in flight in order to perform the TCP function. Then, for the host transmit side, this is more of a pure protocol processing block. It's dealing with all the protocol processing that a transmit driver of a host operating system would require, in particular stateless offloads like checksum calculation and dealing with overlays where they're visible to the host operating system. And we have our virtual switch. This performs the protocol processing and switching the functions that you would require typically by a hypervisor. I think that was OVS. Things like connection tracking, tunnel overlays, and NCAP and DCAP. And this is where our main match action tables live. And then on the receive side, this is the host protocol processing for an operating system, so checksum validation and flow steering. So we actually separate out matching of flows because you'll be doing one level of matching for the switching operation and then matching again under control of the host operating system for flow steering. So if you want, and that's actually key for performance on modern operating systems and very high core count CPUs. And then the receive side DMA is just the converse of the transmit side. Now, the protocol processing components themselves, in particular the host TX and the host RX components, they are implemented directly using the P4 language because P4 is actually perfect for those. And in this regard, this entire pipeline, this entire composable data plane is an instance of the portable NIC architecture. And this is an initiative of the P4 consortium, which Xilinx and Gordon Brebner are big contributors to. each component contains the necessary hardware for the efficient execution of P4 programs. And they can be modified quickly because they're actually expressed in a very high level language, which we may do, or they can be used as a template for customers. Data plane can also be customized on the fly using plugin interfaces, which, there we are, which are illustrated here by, this is the data flow, and it can be, something can be attached to it. So, for example, here I'm attaching additional components, IPsec that's done before or after the virtual switching, and this is how applications can be composed onto what's essentially an existing the networking centric pipeline that I've shown, or you could actually replace an entire component. So you could take data out of the pipeline, pass it through a custom implementation of the virtual switch, and push it back in again, and completely miss out. And that might well be for an environment where the switching needs are just very different from the sort of OVS style switch that we provide. Now, the software tools that are used to construct and control the data plane components are provided by Vitis Networking, and notably, this has got mature support for P4, which is perfect for parse match action processing. It's critical for all the components that handle network protocols. And our P4 implementation natively will infer Xilinx's high performance algorithmic CAM IP to implement the match action tables. So you actually get a really high performance synthesis of P4 kernels. Other languages are supported, and they, as I said, they may be a more natural fit depending on the application component that's been offloaded. And Martin will be showing in a second a pipeline with a TCP component that's constructed using Verilog RTL, an RTL kernel, and HLSC that's performing the kernel offloading of the Ceph distributed object store. It's a very complex application which we're offloading onto the SmartNIC. Vitis Networking also contains the runtime support for managing the data plane composition, so the components can be loaded and unloaded using our underlying dynamic reconfiguration technology. And this can be done while the NIC is online and even passing traffic. And you can have traffic through the NIC, an application starts to run. The flows for that application can be directed to the new components after they've been inserted. And we provide the driver support to control those components at a hardware level. And these are also pushed into the NIC as firmware extensions. So, or we'll pass on to Martin.
My name's Martin Porter. I'm a Vice President of Engineering within Xilinx's data center group. Like Steve, I joined Xilinx through his acquisition of Solarflare. And I've been working on network adapters for over 15 years and in networking for over 25. So let me take over from where Steve left off and talk a little bit about how we use the SmartNIC architecture Steve outlined in Xilinx's SN1000 adapter. So SN1000 is Xilinx's first 100 gig SmartNIC. At its heart, the SN1000 includes an XCU26 UltraScale Plus FPGA, providing over 1 million LUTs of FPGA logic. It couples this with a 16-core ARM for control plane acceleration. The SN1000 provides 16 lanes PCIe Gen 3, Gen 4 to the x86 and includes 2 QSFP28 ports. The SN1000 fully supports composable data flows using the SmartNIC plugin framework and Vitis networking that Steve outlined. However, it also supports a ton of features out the box. Let me dig into a couple of these on the following slides and explain why SN1000 is a great fit for both traditional virtualized deployments and bare metal hosting. The SN1000 can fully offload Open vSwitch, OVS, which is the main software that drives software-defined networking. Both the OVS network data path and OVS control path can be offloaded from the x86 to the SmartNIC. Inside the SmartNIC's network data path is a sophisticated match action engine, what we call the MAE, which is a main switching engine within the SN1000. The headers of each packet are extracted by the MAE, and multiple lookups of the headers are performed in flow tables, implemented as algorithmic CAMs, content addressable memory. And these flow tables can be used for both wildcard lookups for the OVS switching decisions and TCP UDP connection lookups for firewall and connection tracking state. These flow tables reside in DRAM on the SN1000, but are cached within local FPGA memory. This is the match part of the MAE, but based on lookup results, the MAE can be programmed to perform a series of actions on the packets. And the MAE is capable of processing 100 million packets a second of performance, so at very high rates. The SN1000 ships with kernel DPDK drivers that expose standard offload interfaces to OVS. So this results in OVS offloading all its switching and packet manipulations into the SN1000, including the switching decisions, the packet encapsulation and de-encapsulation, such as VXLAN and GRE, any packet edits, and any firewall offload and connection tracking, including NAT, network address translation. Plus, it offers packet replication and replay for telemetry. With OVS offload, the VMs have direct hardware access and suffer no virtualization overhead on their networking data path. For the OVS control plane, we support two models, either more traditionally running OVS on the x86 within a hypervisor or backend OS, or more typically in our customer deployments, OVS running on the ARM subsystem. Therefore, the SN1000 is offloading both the OVS control plane software from the x86 in addition to the data plane offload.
Actually, a question for you there. You mentioned a lot of the extra features. Does anything fancy have to be done within the operating system of the server in order to be able to take advantage of all of these features or some of them?
No, we've tried very hard to fit in with standard Linux kernel interfaces, standard DPDK interfaces. So sometimes there's kernel dependencies because things like connection tracking offload is quite a new Linux kernel support. But generally, load the kernel drivers, which very soon will be upstream in kernel.org, and just out the box, you get OVS offload.
Linux only, or do you have other operating systems that you support for a lot of the newer features?
At the moment, we're focusing on Linux, but we do have a roadmap to support other operating systems.
Cool.
I have a question about the fabric. Do you need switches that have specific capabilities to leverage the smartness of these NICs, or regular off-the-shelf switches are enough to connect these NICs?
No, the SN1000 is 100 gig Ethernet, so just standard 100 gig Ethernet switches is all you need. So this is plain vanilla Ethernet. Okay, VirtIO, as Steve mentioned, is a standard virtualized hardware interface for virtual machines. Includes a number of standard devices, including network and storage devices. One key advantage of VirtIO is drivers are available included for all operating systems. So the drivers are already present in standard customer VM images. So Windows, Linux all have VirtIO drivers. And as Steve mentioned, the SN1000 supports VirtIO natively in hardware in the DMA engine, what VirtIO call VirtQs. So you get this support with no software running on the ARM, so we get full performance on VirtIO network devices. We support two main deployment models for VirtIO Net. Diagram on the left-hand side shows a bare metal server deployment. So in this scenario, the SN1000 exposes PCI functions to the x86, but look and appear as VirtIO Net devices. Both the control plane and the data path of VirtIO is handled by the SN1000. And this can be working in conjunction with OVS offload running on the ARM subsystem. So for example, OVS can request VXLAN encapsulation of all traffic sent on this interface. Xilinx are also actively working within the open source community on what is called VDPA, Virtual Data Path Acceleration, which is shown on the diagram on the right-hand side. VDPA uses hardware support for VirtIONet, but also incorporates changes in QEMU to allow a virtual machine using VirtIONet to get hardware offload. The VM is unaware it's talking to hardware, with the control plane remaining in software. And a really nice feature of VDPA is it allows this VM to still support live migration. We're actively working with a US cloud provider who's very keen on validating SN1000 support for VDPA. And this is attractive to them because the virtual machine has no knowledge of hardware. It has no vendor driver, so it's using standard customer VM images, but the deployment can still use full hardware offload, including OVS, and continue to support VM live migration.
Yes. What hypervisors are supported? Is it just KVM or is VMware also supported?
At launch, just KVM. So in addition to VirtIONet, the SN1000 also supports VirtIO block for storage. The SN1000 can expose PCI functions to the x86 server, which now appear as VirtIO block devices to the OS, and all read-write requests on this block device are proxied to the ARM subsystem. And on the ARM, we provide drivers for the Storage Performance Development Kit, SPDK, and any SPDK storage stack, such as NVMe OF or Ceph over TCP, or a customer proprietary storage stack can be supported. The diagram on this slide shows the power of what Steve was talking about, of application-specific data planes for storage offload on the SN1000. The SN1000 allows the storage path to be offloaded from the ARM subsystem into FPGA logic. And this can be done both using Xilinx supplied or customer developed Vitis kernels. Xilinx provides a Ceph TCP storage Vitis plugin as a reference design. In the diagram, the gray boxes here are the standard SN1000 accelerators, and the dark blue boxes are the Vitis kernel, providing an application-specific composable pipeline. So in this example, TCP is provided as a reusable block by Xilinx, and Ceph is provided in HLS, so C, C++. So it's easily modifiable by the end user and can be adapted if, like some of our customers, they have storage solutions derived from Ceph, and it can also be adapted for any other network file system running over TCP. The SN1000 MAE, its vSwitch, routes packets into this application pipeline. So let me show a quick animation. TCP Ceph accelerators act in tandem to terminate the Ceph protocol with no embedded CPU data plane involvement. By manipulating and processing packets as they pass through the pipeline, the storage control path remains in software running on the ARM subsystem. However, as the storage data manipulation, for example, CRCs, decompression, dedupe, is handled directly by the plugin. And when the I/O is complete, the data can be transferred from on-chip memory or local DDR to the x86. So there's a number of advantages of this approach. No storage payload is passed to the ARM subsystem, providing significant CPU benefits. We get complete hardware offload of the block storage protocols with software-based implementation control and runtime, including the offload of TCP-based storage protocols with comprehensive TCP congestion control. And with both VirtIONet and VirtIO block acceleration, the SN1000 is a perfect solution for bare metal cloud deployments. So Ceph TCP shows the power and flexibility of SN1000 composability. It's a complex application protocol and shows how the SN1000 can offload complex and expressive applications. But this isn't the only offload provided. The SN1000 builds on the many offloads and IPs already provided as part of Vitis. Networking, I've already mentioned some of the OVS and firewall capabilities, and these can be augmented and extended via customer Vitis plugins. Security, including IPsec and KTLS plugins, and storage. In addition to VirtIO blocks, Xilinx has NVMe IP plus a number of other storage offloads. So let me try and summarize. The SN1000 allows software-defined hardware acceleration. It offers line rate performance with P4, C, and C++ for hardware acceleration. And it supports a heterogeneous architecture, allowing control plane offload to be ARM, but with data plane offload directly into logic.
So you mentioned XDP support. So will day one I be able to use Cilium and offload the firewall processing and routing processing into the SN1000?
We support XDP in our kernel drivers, but not on day one are we taking XDP from the kernel and moving that directly into logic, although it's something we are working on our roadmap.
Okay. I had a question on 2 slides ago, 2 or 3 slides ago. What you were describing, I think, as VirtIO net, it looked like what I would call SRIOV, and then on a following slide, you had both of those in a bubble. So I wonder if you can just like quickly give me the difference, because SRIOV is something that has been out and used, for a long time now.
Yeah, SRIOV obviously provides a VF into your virtual machine. And typically with that VF, you run a vendor driver. So for the SN1000, it is something we support. You can run a Xilinx VF driver in your virtual machine. But one problem with that is first of all, your virtual machine needs a Xilinx driver. And also your virtual machine ends up getting knowledge of the hardware and tied to the hardware, and things like live migration become impossible. So VDPA is a little bit different. It does use VFs to provide sort of protected hardware access, but it actually works it works very closely with QEMU, and the VM itself still sees looks to itself like a power virtualized VirtIO net device. It's just when it starts talking to that device, it gets direct access to the hardware. So it gets all the acceleration of SRIOV without some of the downsides of SRIOV.
Thanks. I wonder, is there going to be a place where we can maybe learn more about this after the presentation? Do you guys have links or resources available online?
Yes. Yeah. We have links, and there's quite an active community in the open source around VDPA.
Perfect. Thanks, Martin. Appreciate it.
Who is supposed to do the programming? Is it the customer itself? Is it you that you provide some modules? Will it be done by some software vendors?
So I think the thing to realize is the SN1000 is a full SmartNIC. So out the box, you can plug it in, you can use OVS, you can use VDPA, you can get storage acceleration. You don't need to start programming it to get a lot of those features. If you then want to augment it or add application-specific offloads, then Xilinx are producing some Vitis plugins for the SN1000. But also customers using Vitis framework can start to augment and extend the SmartNIC themselves. So it supports all models of how to use it.
Are there any specific OEMs that you're working with to extend the capabilities as far as like having them develop applications specifically for the card?
Nothing I can mention today, although Xilinx, obviously with the Vitis framework, work with a lot of companies such as ISVs who produce various offloads.
My follow-on question to Wolfgang's question is, can this be programmed or reprogrammed multiple times, or is it a program once and you're done type deal?
No. You can program it as many times as you want. It's just like sort of downloading software onto a CPU. So you can download it, run it, next day decide to augment it with something else. There's no limitations.
Is there any kind of a limit or amount of time taken to reprogram it, or number of times you can reprogram it?
No, it's pretty endless how many times you can reprogram an FPGA. No, there's really no limits at all.